Okay, people are coming in slowly, but I think we can gradually get started here. So yeah, welcome everybody again to the Diffusion Timescales seminar that we've been holding monthly. And for those of you who have not been here before, the format is that we have usually 2 talks, and I'll introduce the talks today right away. The talks are about half an hour each, and after the first talk, you get a chance to ask a few questions. After the second talk, you ask a few questions to the second speaker, but then it's open to start asking questions and discussing on both of the topics. And one of the ideas behind this seminar is that we have a couple of hours. The talks are only 30 minutes or so, so that we have enough time to discuss and cover anything that we need to. Now, before I introduce the speakers today, what I'd like to do briefly is point you to a website that we are kind of developing. It's been an idea that's been around for a long time, but we're finally sort of getting there, where we are putting in a few different resources. So there are software and program that people have developed on doing different kinds of diffusion modeling that are available there. And what that means is, if you have a program, please let us know. We'd be happy to put it up there. Then there will be Excel tables, which we've been meaning to do for, I don't know, Alex was just pointing out, maybe 15 years now, to allow people to just enter, go to a given mineral. If you want to know the diffusion coefficient or something, you can enter that and do that. Then there's a site where we are putting in publications related to diffusion chronometry as they come out. It's a random selection. And so once again, if you have papers, if you are aware of papers, to let us know, and we'll be happy to put those in there. And a few other panels that you'll see. It's a work in progress. A lot of the things are not in place yet, but I just wanted to bring it up in this forum because of 2 things: to make you aware that this exists, but also so that you can contribute to it and send in inputs and help us put the resource together. Okay, so with that, I can go to our speakers today. So we have 2 speakers. Weiran, who goes by the name of Alex, and Smruti Sourav Rout. I'll introduce Alex first, and when I get to Smruti, I'll introduce him at that time. So the titles of the talks are on the shared screen. Hopefully you're seeing that. So Alex will be talking about timescales of magma degassing and ascent revealed by apatite diffusion chronometry. She's been working on different aspects of it for quite some time, so we look forward to hearing to those results. And Smruti will talk about constraints on the dimensional parameters of magma storage as an extended application of diffusion modeling, case study from Taapaca volcano in Chile. And I'll talk more about that when I introduce Smruti. So to just briefly introduce Alex. Alex did her bachelor's and master's degrees in Beijing, in the Peking University. What's interesting in her CV is that for her bachelor's, she actually did a double major with 2 very different things. So she worked on geosciences, but her second major was actually in art history. And so we're very happy that she decided that she wanted to pursue geology rather than art history, and that's why we have her here. And after that, so she completed her master's in 2014, went to Singapore to work with Fidel Costa and did her PhD there, stayed on for a little bit beyond that as a postdoc. During that time, she also visited Bochum to do some experiments. And as of 2021, she is a postdoc at the University of Cambridge. And with that, I'll let Alex pick up a shirt and present a talk. Alex.
Cool, thanks, Sumit. I'll share my screen. Can you see my screen?
Yeah, we're fine.
Cool. Hello, everyone. Firstly, thanks, Sumit, for inviting me to this talk series. And thanks everyone who organized this seminar series. It has been really good talks so far. So my name is Weiran, and most people call me by Alex. Today I would like to talk about using apatite diffusion chronometry to estimate the timescale of magma ascent and degassing. We know that the eruption styles of volcanoes are controlled mainly by two factors: the magmatic volatile budgets, meaning the concentrations of volatiles in magmas, and the other is magma ascent rates. That means the velocity of magma ascent from the shallow magma reservoir towards the ground surface. So knowing the magma ascent rates would allow us to know why there's different eruption styles at volcanoes, and therefore allow us to get a better volcano monitoring, eruption forecasting, and to get better hazard assessments. Diffusion chronometry has been widely used to estimate the timescales of magmatic processes. Here's a plot from Kosa et al. 2020 that summarizes the timescale that can be constrained by different elements in different minerals. I drew this purple box here that shows the timescales of magma degassing at most volcanoes. And then I drew these two red boxes with AP, that means apatite, in the middle of them, showing the timescales that can be constrained by the apatite diffusion chronometry. So this just means that using apatite diffusion chronometry, we can probably get the timescale of magma degassing at most volcanoes. To establish this diffusion chronometry, we have performed experiments. And from these experiments, I want to highlight that we found multi-component diffusion mechanism that I will talk about in following slides. And we also established a diffusion model called AppTimer that can be used to model diffusion profiles in natural samples. So first of all, why do we want to study apatite? What's the use of apatite? Apatite is a calcium phosphate mineral with a hexagonal structure, and it has a special anion site that can incorporate most of the magmatic volatiles, including the three major ones as fluorine, chlorine, hydroxyl. And this plot shows the anion column of apatite that's parallel to the z-axis of the crystal. And there you have fluorine, hydroxyl, and chlorine incorporated. Because of these three components are the major anion components in apatite, the composition of apatite are usually shown in such ternary diagram with these three components as the end members. Here I'm plotting the data from GeoRock. These are the global volcanic apatite compositions. And I filtered this data using a new Python package we wrote called PyApp. Basically, this package can allow you to filter out the data that doesn't pass the stoichiometry test. And so all these colorful data points show those that we consider as good data. And you can probably see that, so the colors means the different tectonic settings for this volcanic apatite. And you can probably see that most of the apatite are fluorine rich, meaning that they're going towards the fluorine end member. This is just a general introduction to apatite composition on Earth. In volcanic rocks that we will focus on today, we have observed apatite appearing in different textural positions, including those as inclusions in melt inclusion, as in shown in this figure here from Erebus volcano and Taapaca. Apatite also appears as inclusions in other major minerals in volcanic rocks, such as amphibole, pyroxenes, and plagioclase. It can also appear as a microphenocrysts or microlites in the ground mass, which is what we will mostly focus on today. We have observed, we have basically analyzed apatites from volcanic rocks from different volcanoes. And then we observed a common feature for apatite microlites from effusive eruption, that they are chlorine zoned. Here I'm just showing one example of apatite in grand mass from the Merapi 2006 eruption. And then this is a backscatter electron image. You can see apatite in this grayish color here. And then we did X-ray maps using electron microprobe for this area. And then you see these chlorine and fluorine X-ray maps. What's outstanding is that these crystals, these apatite crystals, has higher chlorine intensity as shown in this red yellowish color at their crystal rims, but fluorine doesn't seem to show obvious zoning for this crystal. And such chlorine zoning was also observed from maps obtained from ion microprobe. Such chlorine zoning, as I mentioned, was only observed from Merapi 2006 eruption that we studied. And this 2006 eruption is effusive with VI1. For the 2010 eruption, that is more explosive with a VI4, we didn't observe any zoned apatite from the volcanic rocks there. This phenomenon was also observed from Rabaul volcano 2006 eruption. This eruption had 3 phases, including lava flow, volcanic and subclinial phases. Here I'm showing the lava flow apatites has chlorine zoning, as is shown here, and the subclinial phases didn't have any zoning, as shown in this map. Similarly, we found the apatite from Kiel volcano 2007 eruption that's effusive, produced apatite with chlorine zoning, whereas the more explosive eruptions in 1990 and 2014 didn't produce any zoned apatite. So this made us think that the chlorine zone apatite can be related to volcanic eruption size or styles, and that would be really useful for us to understand eruption style changes at volcanoes. So we should do this diffusion modeling to explain such chlorine zoning, but before doing that, I want to talk about whether the zoning we observed are caused by diffusion or growth. And this is, in my opinion, always a big problem or question in diffusion chronometry studies. Here I'm showing one apatite in ground mass from the Rabaul lava flows. And you can see that from the cathodoluminescence image to the upper right corner here. The crystal is probably slightly zoned at the boundary, at the rim, but on the chlorine X-ray maps, you can see the zone has covered a much larger distance. So one of the methods to distinguish diffusion from growth is to look at slow diffusing elements. And in this case, we can look at rare earth elements that were found to diffuse a lot slower than the zoned chlorine. And from the profiles we did using electron microprobe, you can also see that the chlorine is zoned as shown in these red dots, but cerium is not zoned or doesn't show any obvious zoning. So from all this evidence, we can say that the zoning in this crystal was caused by diffusion rather than growth. And with this, we can go ahead to model the timescales from the zoning here. And to do that, we need to know the diffusivity of chlorine in apatite. And here I'm showing a diagram of diffusivity in log units versus temperature. And these are all literature data for different elements diffusion in apatite. And for what we are interested in, chlorine is shown here. It seems to diffuse slightly slower than fluorine and seems to have a strong anisotropy, so a lot faster diffusion parallel to C-axis than A-axis. And these chlorine-fluorine measurements were all from Brennan 1994. And there's also other data for other elemental diffusion in apatite, such as rare earth and other ketones. And you can see that they're a lot slower than the diffusion of chlorine and fluorine at the same temperature. So the question now is that, first of all, what's the diffusion rate of hydroxyl in apatite, as hydroxyl is also one of the three components that's the most abundant anion component in apatite. The other thing is, the other question is, what is the diffusion mechanism of these volatiles in apatite? So to figure that out, we have performed new diffusion experiments and has established a new diffusion model, as I mentioned. This work was published in EPSL in 2020. Now I will just start to talk about how we did these experiments, and hopefully this will be useful for whoever wants to do more experiments on apatite or other minerals. These experiments were all performed or conducted at Bochum. We used two types of gem quality apatites as starting materials. One of the apatites from Durango and is a typical fluoroapatite, and it is always or typically used as apatite standard for different types of analysis. The other type of apatite is from Morocco, and it is less fluorine rich, and it has more chlorine and hydroxyl. So because of the compositional difference between the two types of apatites, we can just put them together to make some diffusion couples and then heat them up in the furnace. So we have two types of diffusion couple. One of them is a more conventional technique called crystal powder couple. So basically we embed a coated, shown here, Durango cube. This is about 2 by 2 by 2 millimeter. And then we put this cube in the powder that's made from Morocco apatites. So here's how the powder looks like. And then here's the crucible where the Durango cube and the Morocco powders were put. And then we put the small crucible into a larger crucible and then put this into the furnace to heat up. The run duration are about within 1 day to about a week. The other type of diffusion couple is called thin film substrate, and this is relatively new technique. So basically, we also deposit powders made from Morocco as a thin layer of particle or material above the polished surface of the Durango apatite. So these two were used for the thin film deposition. And then here's the technique that we use called pulsed laser deposition. And I have a movie here. I hope it's not too loud. So the sound you hear is the laser, the pulse laser that goes from the left side of the instrument and go all the way to the chamber. And then you heat the pellet that's like shown here, heat the pellet and then produce that purple color plasma and then form that thin layer of thin film above the substrate that is of Durango apatite. So that's the technique. And then we put both types of diffusion couples in the furnace, the vertical furnace as is shown here. And we heated them up at magmatic temperature for a series of time durations from 0.6 to 161 hours. After that, we took the samples out and analyzed them to extract the diffusivity. And after this, I will just introduce the techniques we used to analyze the experimental products. So these are the techniques we use. Firstly is the electron microprobe. We use that to analyze the crystal powder diffusion couple. The other two are what we use to analyze the thin film sample, because that analyzing them requires much higher spatial resolution. So we have used SIMS at University of Hawaii and then the accelerator at Rubian Bochum. So here's how the profiles look like. So I'm not going to show all the profiles that we obtained from the three techniques, but I will show the outstanding feature that we observed, which is the uphill chlorine diffusion. So let's firstly look at the results for the crystal powder samples. Here's an X-ray map for the chlorine for a crystal, and then you can see here's the boundary of the crystal, and then we performed profiling parallel to z-axis of this crystal, so along this white arrow direction. And then here I show this similar profiling obtained for 3 crystals that annulled for different time. And you can see that they all show a weird or odd chlorine peaks with about 10 to 20 or 30 micrometers away from the crystal rim. And such chlorine peak, or so-called uphill chlorine diffusion, was usually not observed in single element diffusion profiles. And such uphill chlorine diffusion was also observed from the seam steps profiles that we obtained from the thin film samples. So on the right-hand side, I show the chlorine normalized to oxygen ratio, ion ratio intensity versus the distance, and the distance is in nanometer. So basically we scan the sample from the surface of the thin film and then scan by many cycles until we reach the inside of the substrate. So eventually we got such profiles, and then the distance were converted from cycles of seam scanning using the distance factor correction factors obtained from AFM. So from these profiles, you can also see there is a weird chlorine concentration shown here, which is also a sign of uphill chlorine diffusion. So what is really uphill diffusion? Uphill diffusion has been observed also from garnets in terms of calcium, magnesium, iron, and manganese diffusion with 4 components in that diffusion mechanism. And for basaltic melts, there's also multi-component diffusion that shows uphill diffusion profiles, as you can see here. These are also usually not seen in single component diffusion systems, and it usually just appear in multi-component systems, as for apatite. For apatite, we have fluorine, chlorine, hydroxyl, these 3 components. So apparently they diffuse together, and their diffusion are affected by each other's concentration gradient. Therefore, if we want to model the diffusion or diffusivity of these 3 components, we need to consider the profiles, or we need to look at the profiles of them together. So here I show some classic equations for this flux diffusivity concentration distance relationship. The diffusivity in such multi-component diffusion system is not a single value, but a matrix. For apatite, we consider 3 components. So the matrix is a 2x2 matrix that, because the 3rd component is dependent on the other 2 components. And then any of the element in the matrix can be expressed as a function shown here. And basically what we want to solve is the tracer diffusivity marked in red color here. So what we did was basically taking the results profiles measure for experimental results. And because we know the time duration for each experiment, then we can let the forward model run for certain time to fit the measure profile. So to do that, we need to give the model a series of guessed values for tracer diffusivity. And here I have a video showing what we have done. This is also a MATLAB written code. Here you can see chlorine, fluorine, hydroxyl mole fraction versus distance in micrometer. The black dots are the measured data. The blue dashed line is the initial condition. And then let's watch this again. And then we let the red curve, which is the model profile, to go from time 0 to a given time of the experimental run duration. So if our guessed tracer diffusivity is correct, then we should get the profile fit the measured data perfectly. So this is how we got the tracer diffusivity. If we plot them in a log 10 unit diffusivity versus temperature space, then we can get these Arrhenius relations that are linear, quite linear. And then we see that fluorine diffuses faster than chlorine hydroxyl, and there seems to be a strong anisotropy of chlorine, so a lot faster diffusion parallel to C than the A-axis, which is consistent with what Brennan found. But what's important here, I guess, is that we found a lot slower tracer diffusivity of both fluorine and chlorine than those reported by Brennan in this shaded region or fields. So I think one of the reasons why this happened, so why our diffusivities are slower than Brennan's, could be we consider multi-component diffusion here, which basically means diffusivity are component or concentration dependent, whereas Brennan probably considers single element diffusion. So that could be one of the reasons why there's such a difference. So with the new diffusivities we determined and the model I just introduced in previous slides called AppTimer, we've applied these to natural systems and have got pretty satisfying results. Before showing the results, I want to talk about how the zoning was caused in apatite, why there's zoning, why that's related to magma degassing. So here's just a simple kind of modeling to show why this happened. So if I drew 5 fictive composition of apatite at a given composition in the ternary diagram, if I go from cooling, if I consider cooling during the magma ascent, if I go from 950 degree to 750 degree, I will have the apatite composition go along these trajectories. And then if I consider crystallization of microlites in the melts, that would then increase the fluorine-chlorine water concentration in the melt because they are incompatible. But then with different extents of incompatibility. So that would form or force the apatite composition to go along this green dashed line directions. And then if I consider degassing, and this would mostly happen to water instead of fluorine and chlorine unless the melt reach really low pressure. So under that situation, the apatite composition will go along this blue dashed line direction. So this is kind of it's a very simple sketch, like not considering too many complicated situations, but from this figure, we can kind of compare the directions of each process forcing apatite composition to go with what we really observe from natural samples, which are shown in this red diamonds, that you can see that if we want to go from core composition to rim composition, that's basically along the blue dashed line degassing trend. So that means if that's true, then the timescales of chlorine zoning or chlorine diffusion in apatite are directly related to the timescale of magma degassing. This was then what we observed for the Merapi 2006 eruption. I'm showing just one microphenocryst in the ground mass, and we did a profile along this white arrow direction. This is more or less parallel to the C-axis of the crystal. And then we did the modeling using the AppTimer tool. And then at 900 degree, we obtained 3 timescales of about 2 weeks. And that translates to average magma ascent rates of 0.002 to 0.005 meter per second. If we consider the same depth of magma storage before ascent for the 2010 eruption, because there was no obvious zoning from apatite from that eruption, and then we can get a maximum time scale, which we got as about 5 days. And then that translates to a minimum average magma ascent rates of these values. And these are about 5 to 8 times faster than the magma ascent in 2006. So, which I guess kind of makes sense because because I guess explosive eruptions are expected to have faster magma ascent, and these are also also consistent with magma extrusion rates observed for the 2 eruptions, where for the 2010 eruption, the magma extrusion rate is 10 times faster than that in 2006. So consistent with what we observed using apatite. We have recently applied this method to Rabaul volcano. As I mentioned before, this eruption has 3 phases. And then we have luckily sampled apatites from each of the phases from the same eruption. And we analyzed them. We did some X-ray maps, and we did the diffusion modeling to get a time scale, which then we get very satisfying results. So let's start with the lava flow sample. We got timescales of about 2 months for these samples, and this timescale just agree with the volcano inflation observed a few months before the eruption in October. And then for the sublinear eruption, we observed very short diffusion distance, or nearly no zoning from the apatite from that phase. That corresponds to very short time scale of degassing, a very fast magma ascent. And this time scale all agrees with the seismic amplitude measurements at this exactly same timing from what we observed using apatite. And lastly, there's a Vulcanian phase that happened as the 3rd phase of the eruption. Then for that, we got 20 hours of diffusion timescale that basically falls between the timescales we obtained for the other 2 eruptions. So this just basically shows that the timescales we got from apatite are consistent or match with what's recorded in monitoring data. So these methods are probably useful. So lastly, I want to just introduce our simulation tools for apatite. For what I have talked about in this talk, the AppTimer diffusion model, these are built on MATLAB code, and they will be available on my GitHub soon, I hope this week. And then we have a web version of this modeling tool, and basically you can just simply upload some TXT file or CSV file of your diffusion profile and model the timescale from there. We have some other models based on apatite as well. The PyApp tool that I mentioned in the first few slides are also available on GitHub. It's built on Python. So just to summarize, we established an apatite diffusion chronometry that is useful for estimating the timescale of magma degassing and ascent. And these diffusivities were measured by new diffusion experiments, and we built a new multi-component diffusion model to simulate such diffusion in natural samples. We applied this chronometry to multiple volcanoes, and we have got timescales that really matching with the duration of volcano unrest recorded by monitoring data. Let me see. So I guess there's still some future work that can be done to this method in terms of application of the method. We were all calculating the hydroxyl in apatite using stoichiometry, but it's better to analyze them directly using nanosims or sims. Also, it's probably useful to combine this method with a model that describes the behavioral activity of volatiles in the melt during magma ascent, so that we can probably get a more precise or more accurate model to model the magma ascent timescale. Thank you.
Thank you, Alex. That was a very nice round trip of experiments through to applications and introducing a new tool. So yeah, we can do a few questions and then move to the second talk and then come back to you again. So for those of you who joined late, that's the pattern we have here. So we can take a couple of questions. You can either speak up or write something on the chat and I'll read it out. And then we'll go to the second talk. And after the second talk, we get a chance to discuss both of these together. So if you have any questions, do speak up or type things in.
If I may, a very simple question. How much of the diffusion process could be related to the cooling or during the cooling of the lava flow after the eruption? Is there any significant diffusion at that time, or can you just ignore that and then relate it to the geophysical signals?
Hi, I think, yeah, that's a really good question. Basically, I would think there's very little diffusion going on when the lava flow reached the ground surface at that temperature range. Maybe we're talking about 600 or lower temperatures, and then I'm not showing this Arrhenius relation. You can see that if the diffusivity goes towards really low temperature, then the time scale that requires to get any like water loss or other zoning in the apatite would be really long. So that would then probably unlikely to happen.
Yeah, but it really depends on how thick the lava flow really is. I mean, if you have a very thick lava flow, and this makes it very important where the sample is actually coming from. So maybe it would be a good idea to at least sample from the lavas, the top that is probably faster cooled than the interior. So if you have a lava flow that is, I don't know, 20, 40, 50 meters thick, then you certainly have higher temperatures for much longer time.
Yeah, well, I think it's a good point. Obviously, the outerior of the lava flow cools more or faster than the interior of it. So yeah, it would be a good thing if we can sample the outerior. Actually, I'm not sure which part of the lava flow we sample, but then I think another argument would be the ternary diagram I showed with the trends of different processes that would cause the zoning apatite. If we go, course along this trajectory, that would lead to fluorine-rich apatite, it doesn't appear in any of the apatite that we observed, because most of the apatite we observe has higher chlorine at the rim. That has to go more related to degassing process, I guess. Yeah.
Okay, so next time take a sample from the top and from the center of the flow, and then you know what's.
Yeah, that would be great. Yeah. Okay. Thanks for the question.
Okay, but it's two points come across that. It's always good to know the spatial relation of the samples, and also that you have such different compositional vectors to sort of cross-check afterwards where you're going. So there are different results. So one of the things I was going to ask you also, but maybe we can deal with that after the second talk, is exactly how you do the boundary conditions on this one. So you can think about it while,
Yeah.
So I don't see any other questions here. So I'll let people think about questions. So again, you can ask questions afterwards. And I'll just move on to the second talk to introduce Smruti here. So let me see if I can share my screen again. So yeah, so Smruti is going to talk about constraints on the dimensional parameters of magma storage as an extended application of diffusion modeling, a case study of Taapaca volcano in Chile. And I guess he'll introduce his material himself, but just very quickly, we've been using diffusion chronometry to get residence times, timescales, ascent rates, as you just heard, but we have a relatively weak sense of how big the reservoirs are from which these things are coming, and that's something that Smruti is going to try to address. So to introduce him, Smruti did his undergraduate degrees in India, in IIT Roorkee, where he did his bachelor's and master's as part of an integrated program. And as I found out, he already began looking at diffusion related things during those studies. So after that, he did a year of research assistantship at the Indian Institute of Science in Bangalore, which is Bengaluru now. And from there, he moved to the University of Göttingen in Germany to work with Gerhard Werner on various different volcanoes. He's worked on volcanoes from Eifel, volcanoes from Chile, and he completed his PhD in 2020. And since October of 2020, he's been a postdoc at the University of Kiel, and he does modeling work, some experiments, looks at natural samples, and I'm just curious to hear what he has to talk about today. Smruti, you can, I'll stop sharing and you can pick up the screen.
Yeah, I'll just share the PPT. Yeah, good.
So you can go to the presentation mode.
Yeah.
Yeah.
Okay. Thanks, Sumit, for inviting me. Hi, everyone. So this talk will be about an extended application of diffusion modeling, which is to constrain the dimensional parameters of magma reservoir in the context of Taapaca volcano in Chile. So we all know that constraining the thermal, temporal, as well as dimensional parameters, like for example, the shape and the size of magma systems is one of the main objectives in volcanic research. There are several tools to constrain the thermal as well as the temporal parameters. Like for example, we have thermobarometry and we have absolute dating or diffusion modeling for the temporal aspects. But the constraints on the dimensional aspects are often scarce, unless we have precise geophysical data. And this is much more prominent in the case of silicic systems, which are not always active or may have been active in the past. So, but it's also important to know that the dimensional parameters, however, do control the reservoir's thermal history, and therefore the diffusion history of the minerals which are present. So there exists some kind of relationship. So why not explore this relationship in a well-constrained environment and then see if one can sort of backtrack from the thermal and the temporal parameters to have some kind of constraints on the dimensional parameters. So that is what our objective is. In clear-cut words, we focus on a method that will first constrain the thermal history of a reservoir using thermometric temperature constraints and intercrystal diffusion timescales, and then use those to put dimensional constraints on the storage and mobilization of mushy magma systems. So for that, we take Taapaca as our case study. So Taapaca is a dacitic dome complex in Central Andes, which is a subduction zone volcano. with more than 1.5 million years of eruption activity. Now, Taapaca has produced mostly dacites, which have such large cyanidine megacrates. You can see in these images here. So I'll just give a brief overview of the petrologic implications before we move on to the modeling part. So these cyanidine megacrates are present in almost all the eruptions from Taapaca. They are extremely well zoned in barium, like you can see in this barium intensity map here. And the zones are formed by frequent resorption and regrowth. You can see that each crystal has somewhat up to 15 to 16 distinct zones. And apart from barium and partially strontium and calcium, the composition remains more or less the same from crystal core up until crystal rims. Now, the barium variation in these crystals is interpreted to be direct effects of thermal changes. To the extent that the barium trends can be taken as a proxy for the temperature changes. So, and this is also supported by the intracrystal thermometry. Like, for example, in this case, we calculated temperatures from some mineral inclusions in these crystal zones like amphiboles or plagioclases, which are represented by these red circles, and they match somewhat well with the change up and downs in the barium content. So, and then apart from that, one of the most important things to note here is that these thermal changes that formed the barium patterns here are interpreted to be effects of recharges that underplate and supply heat, but no mass. So absolutely no mixing, but the recharges act as some kind of heat pulses. So that's something important to note here, and that was one of the main interpretations that came from the petrologic and the geochemical analysis of these crystals. And then we applied the diffusion modeling to the zone boundaries in these crystals. So we had zone-specific temperatures constrained by groups of amphiboles and plagioclase inclusions in each zone. And we used a non-isothermal diffusion model, which is modified from Petron et al. To 2016, which gives not only the total crystal residence time, which goes up to 500 kiloyears, but also a interzone diffusion times, which is the time between the formation of two successive zones. So and those interzone diffusion times, they range from 0.4 to 50 kiloyears. And when we look at these interzone timescales between the zones from the crystal cores and the crystal rims, then we notice that the timescales which we get from the cores and the mantles are quite long, and the timescales which we get from the crystal rims are quite short comparatively. So this implies that there is a change in the heat pulse frequency. So that's something quite interesting to see in these crystals and what the diffusion timescale show us. So, and then in the end, when we combine the diffusion timescales with the temperature changes obtained from the barium concentration, using them as a proxy, we sort of get the picture of how the thermal history of these crystals may have looked like before every eruption. So we see that periodic hotter recharges alone keep the system mushy rhyodacite magma reservoir active for a long time at above solidus temperatures. And the storage is marked by multiple intermittent temperature fluctuations like these, which consist of short-term heating and then immediate coolings, which we define as long-term transitional temperature cycling. And then the recharges that cause this temperature fluctuations, they do not exactly mix, but only contribute to the heat budget of the system, and they therefore act only as thermal pulses. And we see that whenever the frequency of the thermal pulses increases to say greater than 0.1 per 1,000 years, then the system seems to heat up. So, and that is outside this short-term heating and cooling intervals, which we term as the mobilization of the system. And then if the frequency increases even further to for example, between 0.3 to 2.5 per 1,000 years, which acts like a critical or a threshold frequency, then mixable or melt-rich magma is produced, which has less than 30% of crystals, which then may go on to mix with the incoming magma, and then may get ultimately may get erupted. So we basically identify these three stages in terms of frequency of the heating events and the overall temperature, and these three stages seem to be controlled by the frequency of the recharges or the heat pulses. So that is what we need to know regarding the petrological implications from the Taapaca cyanidine bergkris, which forms the basis of the model which we'll just see. So after the petrological implications, the next step or the main step was to try and test these conclusions in a model and see how plausible they might be. So first, the basics of the model. So we have so far explored 2D setting. We use a non-convecting Mashi reservoir with more than 40% crystals, and the system interacts conductively with the surrounding, and the governing equation is this, which is just a heat equation, and we have ignored the convection term, and the term here accounts for the heat diffusion, and then we have an additional term which accounts for the latent heat of crystallization. So the capital T here is the temperature, and X is the location, and small t is the time, and D is the heat diffusivity. L is the latent heat of crystallization, C is the specific heat, and phi is the crystallinity of the magma, which we use as a function of temperature from Rayleigh-Peltz modeling. And then theta, the subscript here, just accounts for which medium we are applying the equation to, like for example, the country rock or the magma or the pulse. And then for the magma, we use rhyodacite composition, and the reservoir undergoes frequent or periodic thermal pulses from underneath, which is equivalent to a recharge under plating and then supplying just heat without any mass addition. And then as boundary conditions, like for example, between two different compositions, like for example, between magma and the country rock, we balance the fluxes through this relation, which relates the incoming flux with the outgoing flux. And then the system can either be open or closed based on what kind of flux we have at the grid space boundary. And then these are on the left-hand side are the predefined parameters, most of which we saw already in the equation. And the green table on the right side here are the main variables, starting from the size, shape, and typical orientation of the reservoir, which can mean that whether it's like a sill or a dike. And then that goes on to the same characteristics for the thermal pulse, and then the pulse also has an additional parameter, which is the subshape to account for whether it's a little more flat or a little more rounded shaped. And then how does the model exactly works? So like I said, the system undergoes several periodic thermal pulses at the exact intervals defined by the diffusion modeling. So we start from magma reservoir that starts to cool, and then at predefined intervals we introduce thermal pulse, and then let it cool, interact, and then we apply the next pulse. And then with that, the thermal history of various points within the reservoir is tracked, and either directly compared with the deduced thermal history of the megacrys, or it's applied to plausible starting barium profiles, and then it's allowed to diffuse, and then the resulting diffusion profiles are compared with the actual diffusion profiles we get from the vanadium megacrys. So now we'll see what the outcome looks like. So the primary results based on 2D simulations show that it is possible to sustain a mushy reservoir at above solidus conditions for hundreds of thousands of years only by thermal pulses without any addition of matter at the exact intervals as defined by diffusion modeling. So in this plot, I have this plot from an elliptical system that looks like this, and it has an area of somewhere around, if I'm not wrong, 6 to 7 square kilometers, and then the plot is taken from this point marked by this cross. So you can see that the just like the petrological implications, we can see that we have a temperature fluctuations, and then we have a storage above the solidus temperatures, and the temperature also fluctuates around the vanadium in. It's the temperature where the vanadium begins to crystallize. And then we also see that the pulse frequency plays a key role. When the pulse frequency is increased by 3 to 5 times, then the system starts to heat up. And then when it's increased even more, say more than 10 times, then the temperature is increased above the mush lockup temperature, and then we have the production of melt-rich magma, which has less than 30% of the crystals. And in this, probably the most important thing would be to see here would be that exactly like the petrological implications which we saw earlier, we get 3 stages of the magmatic evolution that may have led to an eruption. And then apart from that, we also see that some specific dimensional parameters of the reservoir as well as the thermal pulse have the distinct impacts on the temperature time history, and therefore on the diffusion timescales. Hence, it would be possible that the model produced temperature and the diffusion trends be compared with what we observe in the samples to sort of get the best fitting set of the dimensional parameters. So, for example, when it comes to the shape and the size of the reservoir, it seems like in a 2D setting, lens or an ellipse-shaped reservoir seems to be the perfect host for the cyanidine macros, and the preferable or the most fitting expanse of that reservoir seems to be 5 to 8 square kilometers. So in this plot on the x-axis, we have the range of the sizes used. So basically the area, and then on the y-axis, we have the fraction of the reservoir where the desired thermal history is observed. So the blue plot here represents where we see the long-term above solidus storage with the cyclic temperature fluctuations, and then the red plot is where we see the slow mobilization of the system again with the cyclic temperature fluctuations. And then you can see that in both of these features, both of them are more prominent in case of an ellipse or a lens compared to a rectangle or a slab. And then similarly, flat subshape, for example, in case of an ellipse, seems to be most fitting subshape for thermal pulse if one were to induce long-term storage with cyclic temperature changes. And flat subshape, like for example, in case of an ellipse, would mean that the major axis is considerably longer compared to the minor axis, and it has a sill-like orientation. And then on the other hand, bulbous subshape, as opposed to the flat subshape, which means that the major axis is more or less equivalent to the minor axis, or even we have a vertical major axis, then that kind of a subshape is more likely to induce heating and produce crystal poor or melt-rich magma instead. So, and broadly speaking, what we see in these things is that these are, of course, controlled by essentially things like the contact surface area and the thickness of the heat source and things like that. But the important thing is that it would be possible to sort of find the best possible set of the shape and the size matches for each condition and for each set of frequency and the corresponding thermal histories. And then apart from that, we also see that the ideal temperatures for the pulses seems to be between 1000 and 1100 degrees Celsius, which also matches well with what we see from the mineral thermometry. But it's the frequency that mainly controls whether the reservoir will undergo long-term above solidus storage, or will heat up to produce a mixable magma or a melt-rich magma. So then after that, in the end, we'll just move on to the last segment of the talk, the conclusions based on what we see so far. So the data so far point towards several distinct but smaller batches of crystal-rich rhyodacite magma in the different physical reservoirs between 3 and 10 kilometers of depth. And then each reservoir undergoes the similar but not the same thermal history and the sequence of events, which is dominated by thermal pulses at particular frequencies, and that continues for the entire 1.5 million years long history of the volcano. And then the storage seems to be controlled by a particular frequency of the thermal pulses that leads to a long-term temperature cycling at above solidus conditions. And the storage regime can also exist for a long time until there is a critical increase in the thermal pulse frequency. And when that critical increase happens, then the system is tipped into the mobilization regime, and that happens within a few tens of kiloyears, and that then leads to the production of melt-rich magma, and then magma mixing. That means the mixing between the resident and the incoming magma, which was so far acting only as a thermal pulse, and then that may lead to an ultimate eruption. And then it's also possible to have constraints on the dimensional parameters of the thermal pulse, which would be specific to each stage of the thermal history. And then in the end, we also see that in terms of methods, the data shows that it may be possible to extend the applications of diffusion modeling to dimensional constraints, provided we have robust intercrystal, temporal, and thermal constraints. And then these are the next steps which we are still working on. This is, of course, a work in progress. And then in the end, I would like to thank you for your attention, and I would also like to thank my collaborators in Bochum, Cutting, Kiel, and Heidelberg. Yeah, thank you.
Well, thank you, Smruti. That was a very comprehensive tour again of the kind of new directions that some of this modeling can take to. And it introduces a lot of new ideas. I hope there are a lot of questions. So once again, everybody, you can just raise your hands or speak up, or just type things into the chat and I will read them out. In the meantime, I'll just point out that Alex has answered one of the questions that Gerhard asked earlier. At least for the Rabaul volcano, turns out she does know where it comes from, the samples, and they happen to be from the top of the lava flow. But yeah, the issue that came up was it's good to know always where things are coming from. So yeah, questions, anybody?
I have a question.
Yeah, go ahead.
Hi.
Hi.
Yeah, pretty interesting. Nice to see lots of people here, some faces I have not seen for a while. In any case, sorry. Yeah, I was wondering, so I think it's pretty interesting. One of the things is I didn't understand is how do you match the volume to the zoning of the barium that you find in terms of the thermal history? I think you did this with these histograms of pink color and blue color, or?
I'm not sure if I understood the
maybe I
question.
put it maybe in another way.
Yeah.
So when you have the thermal model, you have a relatively big volume, and different parts of the volume have different thermal histories.
Yeah.
Right. So then you have to decide which part of the volume you are tracking or to compare.
Yeah.
Right. And so I think in this slide, you show that percentage of the reservoir showing the desired features. This means like percentage of the reservoir with sanding crystals that would show these thermal histories.
Yeah. Yeah. So basically, I start from the bottom and then go up. So of course, in the parts which are closer to the thermal pulse, we see the cycles much more prominently. And as we go up, as we go away from the pulse, we see much less. So it's basically that area. So in case of an ellipse or a lens, we are able to observe that in a much bigger fraction of the reservoir than in case of a slab or a rectangle. In the case of a slab or a rectangle, we see that, but then that can be dominated by something else, like for example, fast cooling or an increase in temperature. So, but what we want to see, which would be an exact match with the petrological implications, then that we see more in the case of lens or an ellipse. So that's what I'm.
Right. I just was trying to.
That makes sense.
Yeah. I was trying to imagine if these things are heated from below. I guess there's a heat wave that comes and goes to the top slowly. Yeah. I mean, what is the vertical? Because everything is vertical extent, no? I mean, the heat comes from the bottom and goes up.
Yeah.
Right. So how long does it take to feel, for example, a wave from the bottom to the top? It must take a long time. If it's all by, it's no convection, it's all by diffusion of heat, no?
Yeah. So as if you're asking the timescales between the introduction of the heat pulse, and then when we see the effect of that, and so that if I'm talking about, say, distance of 200 meters or so, then I do see that just within a few years, it does not take that long.
Okay.
So
Within a decade or so, I see that the pulse effects of the pulse has reached a few hundred meters deep into the system.
So maybe I can try to, I think what Fidel is asking is, how do you track it in different points? So
Okay.
Correct me, Smruti, if I'm wrong. So what you do is you are mapping the temperature time history in a 2D region at different points.
Yeah.
So because it's not convecting, it becomes easier to do that, because you don't have to track a marker. You just fix a point and you track the temperature time history in that point for a given size of reservoir and for a given thermal pulse. And a thermal pulse can be moving from bottom to up. If you're looking at a sill, then it moves from bottom to up. But if you're looking at a dike, then it also spreads out laterally. So that's how the difference in the shape of the thermal pulse comes in. Is that correct, Smruti?
Yeah.
Okay.
Yeah, I just had a difficult time imagining that it seems like the blue is almost 100% of the reservoir shows this. And there should be, I guess, a gradient that is always from below, because the heat comes only from below. And so, yeah, but I guess it's fine.
It becomes much less and less prominent as we go above the reservoir. So of course, at some point we stop to see that.
So the blue Fidel is a fraction of the whole reservoir that shows, and the red is a fraction. It doesn't tell you whether it's at the top or the bottom.
Right.
So most of it is in near the top of, the bottom, of course.
Thank you.
Okay, other questions? So I have a Mike. Yeah, Mike Carroll. Hi, Mike.
Hello, everybody.
Good to see you. Yeah.
Very nice series you've organized here, Sumit. Very, very interesting. Looking at for the last talk, the variation in temperature with time, apparently these magmas spent quite a lot of time above the sanidine liquidus. So these crystals are constantly dissolving. Is that correct? Sanidine crystals have been dissolving for quite a few thousands of years.
Yeah.
Prior to, so there's no sanidine phenocrysts left, only the megacrysts.
Yeah, that's actually quite true. Yeah,
because their large size, they managed to survive longer.
Sorry?
Because of their large size, they managed to survive the long time of temperatures above the sanidine liquidus temperature.
Yeah. Actually, we think that it could actually be the other way around, that because they have undergone such frequent melting and growth, and then it's sort of all the small crystals have melted, and the ones that could survive have grown again and again and again, and they then have become bigger.
Yes, but according to your temperature time diagram, with the blue and the pink and the yellow bands, for the last several thousands of years, they've always been above the sanidine liquidus temperature. So they should have been dissolving a lot.
Okay. Yeah.
I don't have the number of the slide, but I made a copy of it.
Okay.
Yeah, this one.
Yeah. Okay. Yeah. Yeah. this actually because the vanadium N is actually a range of temperatures, because when I did the melts modeling on this, it looks like the vanadium crystallized over a large range of temperatures. So it starts from somewhere around 780 or so, depending on the pressure temperature conditions, and then it goes on to somewhere around 710, 20 or so. So of course, it will depend on the composition of the vanadium, if it melts or grows again, and because it's a range, so it will be not like the crystals will always melt.
Okay. The sanidines are always of constant orthoclase content, or they vary?
No, if we look at the composition, then everything except the compatible trace elements, everything else is the same.
Okay, so they're homogeneous and orthoclase.
Yeah. Of course, there could be an extremely small change, because I think the potassium complements barium, but it's more or less it's the same range. It's I think, if I'm not wrong, it's somewhere around orthoclase 64, 65, somewhere somewhere around that.
Okay, last question. We've done some work, myself and colleagues, about the effects of crystal growth rate on partitioning between sanidine and melt. And we saw that when the crystals grow faster, they're less selective about trace elements like barium. Do you think this could have any effect on your diffusion profiles or your conclusions? If the sanidine barium partitioning is actually related also to crystal growth rate.
That technically would not affect, because the diffusion timescales are not exactly dependent on where the initial concentration is, and we have made sure that these are in fact diffusion profiles, because if we look at the strontium profiles, and we did model a few of them, and those are somewhere around 10 times longer, and they give more or less the same time scales as the barium.
Okay.
So that gives us some level of confidence that these are indeed diffusion profiles, and
yes, because in your first slide you showed the barium crystal, the sanidine crystal with the very large zoning patterns.
Yeah,
and I think when crystals grow fast, they tend to have more melt inclusions in them. So it looks like there are some areas where they have grown quite fast, and other areas where the growth may have been much slower. So that's all. That's made me think of that.
Yes, of course.
Oh, very interesting, though. Thank you.
So
Thank you.
One thing maybe I'll add is that what may get affected is the temperatures that you get from the barium concentrations. The partitioning is getting falsified.
Yeah.
I don't know how big the effect would be, but that may get. Okay, so Gerhard, do you have your hands up, Gerhard?
Yes, if I can. Hi.
Yes, please.
Just a short comment. I mean, I think it's very important to make it very clear that the boundary that was model for diffusion is always a resorption boundary. So we know there is resorption and growth, resorption and growth. So whatever temperature and the solid is and water content or whatever it is, it may be, we observe from the growth texture that there is growth and resorption many times over that change. Now, the point about the growth rate, that would affect the jump in the barium between the resorbed part and the newly grown part. And it probably would have to be a slower growth after the resorption because the temperature would be high. But I'm not sure about that. But anyway, it would only affect the difference in the concentration, not the gradient itself. But Smruti, I have a question to you. How much of the regime changes from the storage to the mobilization and then ultimately to the mixing and eruption, how much of that is actually due to the heat you add over time into the system, so the system heats up, and how much of that is actually dependent on the actual recharge rate? I mean, the external temperature conditions must change through time if you keep adding magma. So there must be sort of two combining effects, and how much is due to which part?
Yeah. So, yeah, if I understand correctly, then you are asking how much of the change between the regimes is dependent on the frequency of the pulses, and how much is dependent on the temperature of the pulses.
No, not the temperature, but the whole system will heat up. And so basically, I can rephrase my question: how much is it due to the frequency of the new pulses, and how much of the heat increase over time is due to the old recharge events that occurred previously? Yeah.
Okay. Yeah. So I think that indirectly depends on the frequency, isn't it? If the frequency is more, then the old and the new will sort of overlap much more. And so I think it's just dependent on that. Of course, if we increase the temperatures, then of course the effects of one single pulse will be much more. But then in that case, we do not see a lot of features which we see. Like, for example, we do not see the cyclic temperatures. Like even though in this regime, when the temperature is increasing, we still see a cyclic change in temperature with heating, cooling, and then it increases on average. But if we increase the temperatures, then that's something we do not see. And I think, as far as I see, based on the specifications which we give for Taapaca, the change between the regimes seems to be mostly controlled by the frequency if we keep everything else constant.
Okay.
Does that answer the question?
Yeah, okay, thank you.
Okay.
So I think, if I may add, just between this and the question Fidel was asking earlier, there'll be a trade-off between the size of the magma chamber and the size of the pulse. And that would be a scaling relation. That'd be interesting to try to find out.
Yeah, And yeah, when that I tried a little bit to look at that, and when that, as far as I see as of now it seems like 25 to 40% of the size of the magma reservoir seems to be a good estimate for the pulse, because if we increase the size of the pulse more than 40% of what the reservoir is, then it seems to be much more dominant, and then we do not see the cyclic change anymore. It just straight away keeps on increasing.
Mm-hmm.
And then if we make it way too smaller, like for example smaller than 25%, then the cycles are way too prominent, and then there is no heating unless we increase the frequency to extremely high.
Okay, so that's very useful, and that would be the kind of thing we need to sort of run by once on 3D to see whether the percentage changes on that or not.
Yeah.
A very short comment on that, because this is very important, because we also need to interpret the same case bar zonation that we observe in large granite bodies. That means that those large granite bodies that have those large megacrystic feldspars with the exact same type of zonation must have formed by a large number of relatively small rhyodacite magma reservoirs, because otherwise you couldn't possibly do this.
If they're formed by diffusion, yes. Mm-hmm. Yeah, that'd be very interesting actually, to try to do it on plutonics. Mm-hmm. Other questions, discussions? If not, I had a question for Alex on the boundary conditions on her thing, same sort of thing. So could you say a little bit about, because your boundary condition would depend on what the surrounding is doing in terms of fluorine, chlorine, and water, and just how you handled it. Could you say a little bit more on that?
Yeah, yeah, I think it's a good question for like possible future work. Basically, I guess we need to consider solubility of different volatiles in the melt during decompression. So basically chlorine, hydroxyl, fluorine, I guess there's probably not that many models that can do the fluorine solubility modeling, I guess. But then I guess that's probably also the challenge. It's probably easier to do water chlorine change, concentration change with pressure decreasing, and then apply that together with the partition coefficients that we already have to the model the boundary condition, I guess, so that change with time.
But what did you do now to do your model?
Yeah, we have done basically actually inverse modeling. So to give a fictive boundary condition that change with time, and then do that forward modeling and use the MCMC to find the best fit or best solution for the time scale with that given boundary change.
Okay.
Yeah, that's what I'm trying.
Okay. I was just curious to know how you did that.
Yeah.
Mm-hmm.
Cool.
Other questions, anybody on anything, either speaker?
Could I say something, Sumit?
Yeah, please, Mike. Mm-hmm.
About chlorine, some magmas which are more chlorine rich, if they're, besides being saturated with a aqueous fluid at low pressure, can also be saturated with a brine phase. In those cases, actually the melt chlorine content increases as pressure decreases.
Mm.
So this could have an effect on your apatite chlorine profiles.
Yeah, yeah, I think
You're
that's
aware of that?
yeah, that's really challenging problem for this model. Or actually, brine can exist in many volcanic systems, and
Yes.
then if they get in touch or in contact with apatite, there might be something that we don't want that to happen, but may happen. Yeah.
But they would control the boundary condition in the sense
Yeah.
of buffering the chlorine content of the melt, which would tend to increase as the pressure decreases. So the apatite is coexisting with the always more chlorine-rich melt as the pressure goes down, as the magma ascends. So
Yeah, I mean, I guess following this, it would be nice to include also apatite fluid partition kind of model that I guess started in like 90s or something, like a long time ago. And then, you know, maybe have like apatite fluid melt as the system to consider partitioning, and then which control the boundary condition. Yeah, that's really challenging, I think. Yeah.
But the ideal thing you want to happen probably is have a brine, but have that brine not be in contact with the apatite, but offer the concentration in the melt. That would be your best situation for your model.
Yeah, yeah.
the most realistic as well.
Yeah,
I don't know, would it?
Be the most realistic as well, probably.
Oh, okay. So maybe that's what you should do. Have the buffer the concentration of the melt with the brine, and then use the melt concentration to the calculation.
Or you could just write a simple equation, simple relation between melt,
exactly. Yeah,
content and pressure.
Yeah. We used it. I did a bit during my PhD, and then it turns out to be like really complicated. Like, as you know, like Webster's work on chlorine in melts. That's like.
But were you making the brine be in contact with the apatite, or were you buffering the melt concentration with the brine?
I guess the latter would be probably easier actually to consider, right? Like make melts as like a buffer between fluid and apatite. Yeah, I'm not sure in like realistically, as Michael mentioned, which case would that be? But I guess like using melt as a buffer is probably a way to model it. Yeah, that's a good point.
Yeah, I mean, if you put it in contact with two different things, it just becomes too messy to be able to handle.
Yeah.
Because you have to worry about mass balance between all of those and everything. So.
Without mentioning sulfate and apatite.
Yeah.
We just need it more complicated.
Yeah. Well,
I imagine it diffuses very slowly. So.
It does. We measured, as you saw, from the slide. Yeah, we measure, I guess it's like kind of between chlorine and hydroxyl, if I remember it correctly. But it was like not the major purpose of our diffusion experiments. So I guess if there's more experiments to be done, that could be better measured, just to see, you know, whether it's like an anisotropy or like diffusion, like how fast it diffuse, like really in different types of apatite, like in, you know, more chlorine-rich apatite or other types of apatite.
Yeah, I mean, getting a window into these volatile elements is really nice.
Right. Very interesting.
Okay, any other thoughts or questions from anyone? Now, I should point out that I don't see all the hands. I'm not seeing everybody on my screen here. So if you're raising your hands and I'm not responding, please just speak up or type something into the chat. So, don't see anything. So I'll just thank everybody once again for being here. And once again, we do this thing, we've been trying to do this thing every fourth Thursday of the month. So we will have a talk in March, and that will be a slightly different format. I'll just end today with that announcement. So what I have managed to do is to ask, I hope you're seeing my screen now. Yes, ask John Brady, because when I look at a lot of things that go on in the volcanology literature, but also many other diffusion modeling things now, that it's had an interesting history, because a lot of these things began in the 60s and the 70s, and there was a lot of activity at the time. Basically, it coincides with microprobe coming into the petrology. People could do spatially resolved analysis and measure profiles. And then it went through a kind of a lull period, and now, obviously all of you are here. There's a lot of activity, but we often don't get to know and hear, what has already been learned. I mean, it turned out people did a lot of thinking in those days, and there are not a lot of those people that are still active. John Brady himself is an emeritus professor, but I asked him to sort of sum up his memories and things of what was going on in the 70s and 60s and 70s and early 80s to tell us a little bit about, and not just diffusion, kinetics in general, as we saw today a little bit, that things like crystal growth and other things just get meshed up with all of these when you start doing the models and things. So it'd be interesting to take a look at that. So that's what it will be. It will be one talk, a longer talk on in March. So with that, I'll say thank you to all of you and goodbye, and we'll stop the session here now. Bye, everybody.
Bye-bye.
But thanks so much.
Thanks, Shumei.